In this lecture, we'll work a couple of examples using the concept of electric potential. Here's the first example. Imagine a region where the electric field is uniform, that is, constant in space and time. The vector electric field is given as shown in SI units. In the same region, we also know the position vectors for locations A, B, and C. Those position vectors in component form are also shown. Let's find the change in electric potential for a path from location A to location C. Stop this video lecture and take a few moments to see if you can determine the answer yourself before continuing. The first step is to notice that since the E field is uniform, we don't need to integrate to find delta V. In particular, the change in electric potential moving from location A to location C is just minus the scalar product of vector E and delta R, where delta R is the displacement vector pointing from A to C. We have the position vectors for A and C, so delta R is just R sub C minus R sub A, which works out to be this. Now, we just take the scalar product of vector E and delta R, do a little math, and end up with this result, that delta V equals minus 600 volts. Notice the units. A volt is a Newton meter per coulomb. For practice, you should try other paths. For example, try delta V for a path from location B to location C. You should find delta V from B to C is also minus 600 volts. Or try also finding delta V from location A to location B. You should find that the change in electric potential from A to B is 0. Here's an example that's a bit more complex. Imagine we have a plate of area A with charge capital Q less than 0 spread uniformly over the plate. Let's choose our coordinate axes like this, with the y-axis perpendicular to the plate. Near this negatively charged plate, we have a plastic spherical shell uniformly covered on the surface with positive charge capital Q sub S. Let's find the change in electric potential on a path from location I to location F as shown, where location I is at the center of the sphere and location F is outside the shell. But like the shell, location F is also close to the plate. Now, locations I and F differ only by their separation along the y-axis. The 2 points are a distance d apart. The problem looks a bit challenging at first. The key here is to use the idea of superposition, namely, the total change in potential, in electric potential, from I to F will be the sum of the changes in potential due to the plate and the change in potential due to the shell. So we're going to focus on the plate first, ignoring the shell, and calculate delta V due to the plate, then focus on the shell, ignoring the plate, to find delta V for the shell, and at the end, add everything up. First, the plate. We found from our earlier work that the electric field near a plate is this, for the plate oriented as shown. Recall that the field near the plate is perpendicular to the plate. That means here the electric field has a non-zero component only along the y-axis. For a negatively charged plate, the electric field points toward the plate. Double check to make sure our expression for the electric field correctly describes a field pointing toward the plate, that is in the plus y direction. We notice that this E field is constant, so the change in electric potential for the plate is just minus the scalar product of that electric field with delta R, the displacement vector that points from I to F. Here's how to write down delta R in this coordinate system. So we can take the scalar product and find delta V due to the plate. Notice this is greater than 0, which makes sense because delta V is always positive when the displacement is pointed oppositely to the electric field. Now let's find delta V for the charged spherical shell. Recall that inside the shell, which is uniformly charged, the electric field is 0, and that outside the shell, the electric field looks like that for a point charge with the total charge here, capital Q sub S, located at the center of the shell. So in finding delta V of the shell, which is the electric potential at F minus the electric potential at I, we'll consider an intermediate location on the surface of the shell at radius R. Breaking up the path into two parts, we first go from location I to the location at the surface. The potential difference for that is V sub R minus V sub I. And the second part of the path is from the surface to location F. The potential difference for that piece is V sub F minus V sub R. The sum of these gives the total change in electric potential for the shell. Now notice that since vector E is 0 inside the shell, the potential difference inside the shell is 0. So all we need to focus on is the potential difference outside the shell, where the shell's E field looks like a point charge. We know how to compute the electric potential difference for a point charge, here starting at the surface of the shell and ending at location F. And here's the result. And this is the change in electric potential for the shell between location I and location F. And notice that this is less than 0. Now we just have to pull all these results together. Sum up our two results for the plate and the shell, and here is the final result. That's it for this lecture. In our next lecture, we'll begin to use the concepts of electric potential to describe electrical circuits.